Today's contestants are the Alta Maker 3, the original Prusa i3 Mark III, the Creality Endor 3, the B3N Sigma R17, and the Lowspot Min 3. Anyways, today I'll be doing some heated bed testing. I'll be doing some myth busting, doing some measurements on these heated beds. We're going to be looking into whether we actually need one, what they do, what the differences are between the buildups that these machines have. This is an aluminum PCB. This is a PCB with glass on top. There are different stack ups that use all sorts of different combinations of materials and how they perform. Whether your heated bed is lying to you by showing you a higher temperature, how resistant, where did my fan go? How resistant these types of heated beds are against air blowing over them from a fan. This is my, standardized heated bed testing pod. And much more. I'll be using a FLIR thermal camera. This thing connects to my phone. We're going to be getting some beautiful thermal images from this. And yeah, you're going to learn how these different beds perform. Let's go. So first of all, what does a heated bed do, and do you even need one? Now, the understanding today is that with PLA, there are so many different and actually quite good bed surfaces that you can have in your printer that can get a PLA filament to stick to any surface, even if it's not heated. And my experience with those is that, yes, they can work. They can actually give you good results with smaller prints, like, 4 inches, 10 centimeters, something like that can work pretty well without any sort of heat added. However, there is a clear advantage of having a heated bed. First of all, you can have a permanent surface on there that you can use for many prints in a row without doing anything to it, without renewing it. But also it makes larger prints possible that would otherwise kind of start to warp up or pop off during a print if you're unlucky. And that action of the print popping off is something that a heated bed can actually give you intentionally after a print, because as we all know, when stuff heats up, it expands, and as it cools back down, it contracts. So if your print is on a heated bed and it's warm and at the end of the print it cools down, it just naturally tries to pull itself off the bed. So even for PLA, I would always recommend going with a heated bed. It just makes life so much easier. But as soon as you move on to PETGs or ABS or polycarbonates, nylons, those filaments, a heated bed is just an absolute necessity at that point. Hey, it's Tom from the future. I've traveled through the quantum realm to tell you that current Tom has figured out that this video you're watching would have been 35 minutes long, which is obviously, considering the average YouTube viewer's attention span, way too long. So I'm splitting this up into 2 parts. We're going to be doing some of the more involved tests in the next video, but for this video, we're also going to be doing some really interesting stuff. So let me tell you what that's going to be. So in this video, we're going to be looking at heat up times. We're going to be looking at, how even the heat up is. You're going to be seeing all the nice fancy thermal patterns that we see on these beds, and some of them are quite fascinating. We're going to do some subjective evenness measurement. In the next video, we're going to be plopping this fan on the heated bed to simulate a part cooling fan blowing over the surface. And we're also going to be looking, at whether the beds stabilize, how they change during a print, so about 10 minutes after they've hit their nominal temperature. That's going to be next video. But yeah, for this one, heat up times, thermal patterns, and whether your bed is lying to you. So before we get started with that, let me show you what the differences are in how these beds are built, because there is quite a difference, and I've picked these 5 machines for a reason. So starting with the Alta Maker. So the Alta Maker's base is a 1.6 millimeter, so relatively thin aluminum PCB. So the heating traces are on the bottom, and then you have this 3 millimeter piece of glass clamped on top. There is no air gap. In fact, these are spring clips, so these make sure that the bed is just clamped down really well. So that's the Alta Maker, has that heater PCB and a piece of glass on top. Now, if we compare that to the other extreme, which is the Lowspot Mini, we can see that this is quite a different buildup. So the first one is the type of heater. So while the Alta Maker uses a PCB, a sheet of aluminum with traces on the bottom, this is using a silicone heater. So there's heater wire embedded in a silicone mat, and that is directly stuck to a piece of glass. So it's not laid on top, but it's directly bonded with some adhesive film to that. The glass in here is also 3-ish millimeters thick, and then there's a film of PEI on top here. So just to give you a perspective of why this matters, we should look at the thermal conductivity of these different materials. So we start at aluminum at the very bottom here. So aluminum has about 230, 240 watts per meter Kelvin. The higher that number is, the more easily heat is going to move through that material. So that means heat will spread out very nicely and very easily, but it's also not going to be much resistance to travel from the bottom where the traces are to the top where your print is actually going to stick, or it has to stick. So typically high thermal conductivity, very good. Aluminum is about 230 watts per meter Kelvin. Glass is 0.76, so a factor of 300 worse than aluminum. So yeah, that is something to keep in mind. Because the Low Spot Mini does not have any aluminum in here, or any other metal, the only things that will spread or transport the heat is the glass itself and the silicone. Plastics, by the way, are around 0.2 watt per meter Kelvin, so a factor of over 1,000 worse than aluminum. So I'm not expecting this Low Spot Mini's bed to be very evenly heated up, simply because, well, there are discrete heater wires in the silicone mat, and the glass does nothing to spread the heat. So we're going to be looking into that and what other funky things we see in this heated bed. Now, these other beds are basically just variations of those same three materials. If you look at the Ender 3, the Ender 3 has the same type of aluminum PCB as a heater that we see in the Alta Maker. This one is a bit thicker. This one is, I think, 3 millimeters. This might actually be 4, I don't know. 3 millimeters, and then this plastic film on top. So that plastic film, even though it is pretty thin, will be a bit of an insulator. But because the aluminum is so thick, I expect this thing to be really even and to have no like singular hot or cold spots. So that's the Ender 3, really simple setup. On the Prusa, you can actually see that PCB and what that looks like, and you can actually see the traces themselves. You can see that pattern up top here. So this is the actual PCB. It's not an aluminum core PCB like the Alta Maker or the Ender 3. This is just a regular FR4, so a composite material heated bed. And then we have this spring steel sheet. It's coated with PEI on both sides. So yeah, we don't have any... We don't have any aluminum here that would spread the heat, but we do have this steel sheet. Steel is not as good a conductor of heat as aluminum, but it's nowhere near as bad as glass. Let me look it up real quick. So yeah, steel is somewhere in the 40 watts per meter Kelvin. So still a lot worse than aluminum, but at least it's more than 1. Glass is 0.76. So this should even out the heat slightly, but not as good as the aluminum bed on the Ender 3. So we're gonna be looking into that. And then lastly, we have the Sigma, which is kind of a hybrid between what the... So yeah, this is kind of a hybrid between what the Prusa is doing and what the Alta Maker is showing. So we have the same sort of heater PCB that the Prusa has with the traces, I believe, on the bottom. And then we have a glass sheet that just snaps on top here. And the interesting thing with the Sigma is there is a bit of an air gap between this glass sheet and the PCB. So it doesn't make physical contact. It's not touching down. And we're going to be looking into how much of a difference that makes. All right. Back to Tom from the past. Okay, so I hope that sorted out what exactly we're going to be testing for here and what we're not going to be testing for. I mean, there may be a lot of things that I could have looked into, but just to keep the scope of this test kind of compact, I'm not going to be looking at, what insulation on the bottom of a bed does. I'm not going to be modding anything. Well, except for maybe this glass bed on the Alta Maker and on the Sigma, because if you just look at it with a floor camera, with an optical camera, this stuff is reflective, this stuff is glossy, so you're going to be taking measurements of the environment. So I'll need to spray paint this with a matte color. So let's go do that, and then let's do some tests on these heated beds. Alright, let's look at how the Alta Maker 3 heats up. And overall, it's actually rather unspectacular. What I am noticing is that the edges of the heated bed seem to be rather well heated. It's almost like there's a bit more power on those outer rims. And it also looks like the right half of my heated bed is defective or not heating up as much because there's a big cold spot there. If you take the numbers there, it's not as drastic as the colors seem to suggest, but overall it's something to keep in mind. Temperature tracking during heat up was actually quite good. The temperatures that the Alta Maker displayed were always very close to what I saw on the FLIR camera. Now, one quirk that I noticed was that the Alta Maker 3 actually never reached 60 degrees on its internal readout. It was hovering at about 59 degrees for quite a while, and 2 minutes in, I just decided to call it a day and that it was now heated up. But going by the Alta Maker 3's display, it never actually reached those 60 degrees. The surface temperature did overshoot those 60 degrees to about 64 degrees and then settled back into 62, but overall, it was quite good. All things considered, it took the Alta Maker 3 about 4 minutes to reach 60, or well, 59 degrees, which is on the slow side, but still very usable. Next up, the Ender 3, and isn't thermal imaging just a beautiful thing? Look at it glow. Now, the Ender 3 is what you would expect from a typical heated bed. It heats up very fast in the center, the edges are a bit cooler because the heating traces don't go all the way to the edge and there's a bit more cooling happening just from convection there. And what you can actually see with the Ender 3 is that those 4 screw holes where you have the adjustment points for the heated bed, those are actually screw heads poking all the way through the aluminum plate. You can very visibly see those. They do have a cooling effect on those very spots. One thing that I noticed with the Ender 3 is that the reading on the LCD screen on the firmware was actually way too low for the temperature the heated bed was already at. So for example, when the printer was displaying 50 degrees, the heated bed was actually already at 57 degrees Celsius on the surface. If you're wondering what my hand is doing, I'm gesturing out what the temperature readout is because I wasn't sure if it was going to be legible in the video. The Ender 3 took 2 minutes 24 seconds to heat to 60 degrees, which is very good. After it was done heating, it did overshoot to 65 degrees Celsius, but it did settle in to a more reasonable temperature after a few minutes. Now, the original Prusa i3 Mark III by Joseph Prusa is actually quite interesting in how it heats up, because the Mark III is advertised with a very power heated bed. Now, the Alta Maker might have one too, I haven't looked into that, but it's certainly not being advertised. And what the Mark III is doing is that its heated bed has heating traces that produce more heat towards the edge of the bed to make up for that cooling effect that we saw, for example, with the Ender 3. Now, what you can definitely see with the Mark III are the 9 screws that go through the bed and into the undercarriage, as well as the 4 calibration points, one in each corner. The calibration points don't have any heating traces there, and the screw holes just suck a bit of heat down onto the aluminum undersheet. And then there are hot zones in the very front and very back of the printer. And then the very center of the bed, where I always put my readout on the FLIR camera, is actually the coolest spot on the entire bed. Now that spot is very close to what the printer is reading, so that reading is pretty accurate, but the temperature difference during heat up is about 5 degrees Celsius, and the overall heat up time until the printer reads 60 degrees is 2 minutes and 17 seconds. Alright, now the LoadSpot Mini. Now this is a really interesting one because it's a bed setup that almost no other printer uses. It's a silicone heater that is taped directly to a sheet of glass and then has a sheet of PEI stuck on top to give it some adhesion. And if you look at the pattern that silicone heater produces, it is quite fascinating. So what we can see is that the heating wire inside the silicone heater is actually going from top to bottom in this view. And it looks like there are 3 connecting, alignment tools in there that seem to block the heat from those heater wires. There's also a big notch on the very left side of the heated bed. That is where the connecting wires are attached and where the thermistor sits. So that's going to be a bit of an issue with thermal accuracy. Now what's interesting is that even though we have this weird pattern on here, it looks like the heat up is fairly even, at least in those 4 zones where it is heating up. The only outlier here is the second one from the bottom. That is where that silicone heater has already started to bubble off of the glass and kind of peel away. It's almost like the adhesive is giving out from the heat and then just keeps degrading even more in that one spot. Now, to be fair, that is not exclusive to glass beds. That is also happening on aluminum beds. It's just that aluminum isn't transparent, so you're not going to see it. But with a glass bed, you do see those flaws. Heat up time with the LoadSpot Mini was 2 minutes and 30 seconds, so very good. Keep in mind, this is a smaller heated bed. This is just 15 by 15 centimeters, so the same amount of power as a full-size bed can heat up the smaller one much, much faster. Now, the interesting thing is that the LoadSpot Mini actually overshot by quite a bit. The heated bed's surface temperature peaked at 75 degrees. And I think the reason for that is that the thermistor is actually getting cooled by having contact with that bottom supporting aluminum plate, so it will always read a lower temperature than it is actually at. So that is something to keep in mind with the LulzBot Mini. Alright, next up, the BCN3D Sigma R17. Now, this is not the very most recent model they have. They have the R19, and I'm not sure what they changed with this heated bed setup, but this one is wild. Alright, so it looks like there are 4 heater zones, but in reality, I think it's only 2. So there's a front and there's a back heater zone, and there's a bit of a divide between them. Now, the very front notch that you can see, that's where the heated bed has its magnetic, alignment ball that snaps down into the bed. So there are no heating traces there, which means the temperature is going to be cooler. Now, because of the unique setup of the Sigma, where the glass bed is not actually touching the PCB, and there's actually an air gap between that glass sheet and the heater, there's a massive offset between what the printer is displaying and what the surface temperature is of that heated bed. At times, the offset was at 20 degrees Celsius, so when the printer thought it was at 60 degrees, the surface was actually just at 40 degrees Celsius, which is clearly an issue. The other unique part about this heated bed is that the front and front right corner were actually heating up much faster and much hotter than the rest of the heated bed. Now, the very center where I have my spot measurement on the camera is actually one of the coldest spots on the bed, and there was an offset of about 10 degrees between the center and the hottest spot in the front right corner. Now, the printer thinks it's at temperature way before the surface has actually reached that nominal 60 degrees, and it takes about 7 minutes for everything to equalize to like a usable state. So it does crawl up to those 60 degrees eventually. So obviously there's no overshoot, so it never exceeds that set temperature, and it never really equalizes. There's a 5 to 10 degree difference between the center and that hot spot in the front right corner. So while the heated bed is definitely usable, because it does get hot, it's by far the worst performance so far. It's slow and it's really uneven. Hey, it's Future Tom again. So I want to sum up these results that we saw with all these tests, because I think we did learn a lot. So first of all, heat up time. It's interesting to see that grouping of between 2 minutes 15 and 2 minutes 30, where 3 of the machines fall in. So the Prusa was like 217, the Ender was like 220 something, and the LulzBot Mini was 230, or the other way around. But they were all in that 215, 230 to 60 degree range. And it's interesting to see. Man, Future Tom, why did you have to record a 25-minute outro? I can't edit this down, and your job was to keep it short. This is gonna have to go. Okay, maybe let's swap this one out and get it in there up here. So yeah, looking at the results here, let's do this fast. So heat up times were all between 215 and 230 for like the normal printers. The Alta Maker and the Sigma were a bit slower, but still within reason. But really tight grouping on these. Next up, accuracy and overshoot. These printers were all within reason. They were all, within 5 degrees, let's say, except for the LulzBot Mini, which has the thermistor touching that aluminum plate below it. So that is getting cooled and displays just a completely wrong temperature and heats up to the wrong temperature as well. The Mark III has that glossy bed, so I don't think the readings were accurate, but overall it's probably within range with everything else. Next up, how even were the beds? They were all fairly usable. What I think we did see is that whenever a heated bed has some sort of aluminum in it, whether that's an aluminum bed with the Ender or a aluminum PCB and then glass on top with the Alta Maker, that really helps to spread out the heat and give you a more even surface. Something like the LulzBot Mini, where there was no heat spreader, where it's just a silicone with glass, is really spotty and really uneven. The Prusa with its steel sheet was somewhere in between, but still usable. The other thing is edge cooling, how much the edges and corners cool off. And with a very power heated bed, which the Prusa and the Alta Maker employ, that really helps a lot. You also need good heat transfer from your heater to the bed. So what the Sigma is doing with that air gap between the bed and the actual heater, that is just destructive to having an even surface. But yeah, I think most of these printers had a build area that was pretty close to the advertised one, or pretty close to the surface. On most of them, if you just leave out like the last 2 centimeters, the last inch away from the corner, then you are good even with higher temperature materials, except for the Sigma. So if I were to rank all these heated beds, I would say the Alta Maker comes first. because it has such nice hot edges, even though there's a bit of a cold spot in the right half, but it's not too drastic. It takes a bit longer to heat up, but it's really even and the entire surface is just perfectly usable. So for me, that is the winner in this round. Second place would be the Prusa, I guess, because it's still very even. It's a bit more spotty, but it's still, you know, very usable. You get a lot of space out of that 25 by 20 centimeter build envelope, or 21 centimeter. Third place, I think, is a tie between the Ender 3 and the Low Spot Mini. The Ender 3 has a lot of corner cooling because it doesn't have any sort of heating zone arrangement, so the corners do get cold, whereas the Low Spot does not track temperature accurately, but doesn't have that corner cooling effect, although it's still not a very even heat distribution across that bed. And the clear loser of this comparison is what the Sigma is doing with the heater PCB and then an air gap tube sheet of glass. That is just that's just the worst of all worlds. It's slow, it's uneven, the corners are unusable, the temperature offset is horrible unless you give it some more time to heat up. That's going to be part 2 of this video. So that's last place. I think we could go a long way with the Sigma's bed by just taking out those spacers that kind of keep the glass sheet above the heater PCB and just dropping it directly onto the surface. That would probably help tremendously with evenness and heat up times and accuracy and all those things. But yeah, that's something that maybe if you have a Sigma you can mod. You can just maybe even just flip the bed around. So I hope this part 1 of the heated bed comparison series was helpful to you. We're still going to be doing part 2 where we're going to put a fan on top, where we're going to look accurately at, you know, how even these heated beds are and what the actual minimum and maximum temperatures are after they've heated up and once they've settled in. So yeah, if you want to check out any of the printers or the FLIR thermal camera that I used, those are all linked in the video description below. The FLIR camera is a bit expensive, but they do make a cheaper version. Thank you for watching. Thank you for supporting the channel on Patreon and through other means. And I will see you all in the next one. Goodbye.